topic, I was thinking about if you're in science, in a science lab setting, it could be biology, it could be, I don't know about physics, but you might deal with a solution like a chemical, and you need to know how concentrated that chemical is. And so it's not just a chemistry thing, okay? So today we're going to talk about how concentrated solutions are. So solutions actually are just a type of mixture. So we said matter can be a pure substance, and if it's pure, it can be an element or a compound, or it can be a mixture. And if it's if it's well mixed, it's a homogeneous mixture, and actually solutions are types of homogeneous mixtures. That's it. Okay, it's the same throughout. No big surprise there. So solutions, we have a lot of S's, and I kind of complain about things that sound similar. So if this is my beaker, okay, I have a lot of something, and that lot of something I have is the solvent. And then to that solvent that we have a lot of, we add the solute. Okay, so solvent plus solute is equal to solution. Yes. Exactly. You got it. Now, if the solvent is water, which it doesn't have to be, then we have an aqueous solution. Okay, so that's it. A lot of aqueous solutions out there. Water is a wonderful compound. It's just amazing how wonderful it is. So the scenario I just drew where we had the liquid solvent, okay, and we added kind of something powdered, the solute, and made up a solution, okay? That's what we think of, but it doesn't have to be that way. If you drink soda pop, okay, one of the things in your soda pop that makes it so wonderful is that fizzy stuff. Yeah.
I don't like pop.
You don't like pop?
That's what I don't
Oh,
like.
I crave it.
It's like
The fizz?
yeah.
Maybe one of these days you'll like it. I don't know. But that fizz is carbon dioxide, and so that's a solute. Okay. And then we have a liquid. You can use liquid solutes and kind of dilute them up. And also, as we're walking around this room, it's about 80-20 nitrogen, oxygen. So it's a mixture, and so it's a solution. Okay. And then this is one of my favorites, is you may know stainless steel, for instance, you can get different grades of it that has different, an assortment of elements in different amounts, okay? So stainless steel actually is a frozen solution, okay? Basically, those cute little metals of different types are frozen together. Yeah. What's that?
Probably molybdenum.
Mm-hmm, yep. Molybdenum, yep. So I think that's kind of interesting. So like I said, you know, oftentimes in life we need to say how concentrated something is. And today we're going to talk about 2 ways to say how concentrated a solution is. And so oftentimes the two things we're going to, is that outside? Okay. All right. The 2 things we're going to talk about is the amount of solute, I think a hee-haw, per a given amount of solution. Okay, and actually we're going to do grams of solute per liter of solution, and we're going to use moles of solute per liter of solution. But that's what we're going to focus on. In actually not till general chemistry 2, the way I teach it, we do how concentrated is a solution in terms of moles of solute per mass of solvent, which is kind of weird. Okay, so you're probably familiar with the terms concentrated and dilute. They're just generic. You know, somebody says I have concentrated sulfuric acid, you're kind of more respectful of it than if somebody says I have nitric or a dilute solution of acid. So, okay. So here's the numbers part. Grams of solute per liter of solution, okay, and moles of solute per liter of solution. So those are the 2 I want to talk about today. When you guys did your sodium bicarbonate last Thursday, the HCl in the hood was, I think, was 2.0 m. That m stood for its molarity. So So if you have solution in the bottom, in the first case, we're going to have grams of solute, and we're going to definitely want to unpack these. So G of solute, clearly in the numerator, divided by or per 1 liter of solution. Solution I abbreviate SOL apostrophe N. And the other one is moles of solute. And remember, we know how to get moles. We just have to use the molar mass of something. So moles of solute per 1 liter of solution. And like I said, that is molarity, the capital M. But one of the things we talked about before, and you already know this, if you put a can of pop in the freezer, it'll explode. It's not because of the carbon dioxide, what?
Or in a hot car.
Or in a hot car, yeah. So sounds like that's from experience.
Yes.
Oh dear.
Unfortunately.
Okay, no. Well, hot cars may be a better example. Things as they get warmer expand, okay? And apparently it expanded beyond the strength of the can you had it in. Okay.
All
So-
over the back.
So volumes are kind of a moving target with regard to temperature. So these two actually, if you say how concentrated something is, you have to say at what temperature. And usually we just go with 20 degrees Celsius. So kind of plus or minus 20 degrees Celsius. Liquid water doesn't change its volume. So that's pretty good. All right, so let's do an example, and we're going to make sugar water. And the formula for sugar or sucrose is 12 carbons, 22 hydrogens, and 11 oxygens. So we're going to come up with how concentrated this sugar solution is, both in grams of sucrose per liter of solution and in moles of sucrose per liter of solution. So we're going to knock it out. So what I would usually do, and I think I'll go ahead and draw it on the board this time, is draw a picture. And in my picture, I put my information. So my beakers are kind of lacking sometimes. Okay, there's my solvent. Okay, here's my solute. And if I look at what it is, okay, so I'm going 32.2 grams of sucrose. I'll go ahead and call it C12H22O11. Is dissolved in, my final solution volume is 225 milliliters. Well, that's terrible. Okay. So with this picture here, see the question is, let's see, what is the concentration in grams per liter? So I can write maybe question mark, what I'm after, and write grams of C12H22O11 per 1 liter of solution. So that's what that means. What is the concentration? So this is where I say don't make it harder than it is. If it looks like I can just take this mass and divide it by that volume, you're right. That's exactly what I'm going to do. Okay? Now granted that volume is in milliliters, not liters, but I'm going to fix that. Solution, no pun intended, is to simply take that mass, that 32.3 grams, and divide it by my solution volume, 225 milliliters of solution. Now if I were to stop there, my units wouldn't be right. So this is where, if I want to get my units of milliliters to cancel, I'll put units of milliliters up here, I'll put units of liters down here. Now this is a really common missed conversion. I've done it before. Okay, so, but there is 1 liter contains 1,000 milliliters. So that's a very common problem. But if I do that, I guess more specifically I should put milliliters as solution, shouldn't I? And if I do that, you notice my milliliters of solution cancel, and I'm left with the units I need to be left with. That's my question. And that's done. So we need to round to how many significant figures? 3. I'm liking it. So that's it. 144 grams of C12H22O11 per 1 liter or over 1 liter of solution. More commonly written, maybe, if you're not using it in a problem, is simply G/L. So 144 G/L, and then you have to say what your solute is. Sucrose, C12H22O11. That works. How concentrated is the solution? Okay. So we're going to piggyback on that answer and get the other way to express how it's concentrated in moles of sucrose per liter of solution. Now, if I didn't have this 144 first, I would go ahead and start from scratch. Okay. And we'll do, I think, an example of that coming up. But now, if I'm after molarity, okay, so I filled in this question mark, 144 grams of C12H22O11 per 1 liter solution. That's what I got. And now what I want, question mark, what I'm after, is moles of C12H22O11 per 1 liter of solution. So do you see where my denominator's ready? All I got to do is fix my grams to moles. That's it. And we've done that before a few times. I can go from grams in the numerator or top to moles in the numerator or top just by inserting next to that 144 grams per liter, just by inserting its molar mass. So here's the molar mass of C12H22O11. So I take 12 times 12.01 plus 22 times 1.008 for the hydrogen, plus 11 times 16.00 for the oxygen. It's a pretty darn heavy molecule, but it's just the tip of the iceberg for biomolecules. So 342.30 grams per mole. So I'm going to go ahead. Does this make sense? Okay. If I want grams to cancel on this next term, I'm going to put grams down here. I want to be left with moles. So do we flip the 342.30 or do we leave it the same? We flip it. Yep. Okay. That's exactly it. So if we start with the 144 grams, and this is where if you wanted to abbreviate it sucrose or whatever, but 144 grams of C12H22O11 per 1 liter of solution, and then insert the molar mass, 1 mole of C12H22O11 over 342.30 grams of C12H22O11. Notice our grams cancel, we're left with units of moles per liter, and that's what molarity is. So how many sig figs? Everybody's tired. How many sig figs? 3. Yep. 3 sig figs. And I probably would just use I would tidy it up with the big M. I would put 3 sig figs gives me 0.419. I would put a big M for molarity, and then I would put what the solute is, C12H22O11. Not bad. I don't know if you want to get it in your notes. I mentioned if we didn't have the 144, if we were just going for the molarity, given the original information, which were these 2 blue numbers, okay? I'm going to kind of show you how I would work that, molarity. I would go with the mass, and you get the same number. I would go with the mass, 32.2 grams over 225 milliliters. Okay, I would know that I need to go ahead, I need to get my grams to moles, and I need to fix my milliliters to liters. So however you want to do that first. Let's go ahead and fix my milliliters to liters like we did before to get the grams per liter. If I do 1,000 milliliters over 1 liter, that fixes my milliliters. And then if I go ahead and insert now the molar mass, you told me to use the flipped version, which is right, 1 mole over 342.30 grams. Now my grams cancel, okay? Unit-wise, I have moles per liter. So this actually, you get the same answer. This right here was our 144. Okay, so that's just if you didn't have to go through grams per liter. You want to go right to moles per liter. That might help you for some of your homework. Well, I still try to play these movies. They're just not playing for me this semester. But we have a still image of this one. So somebody was tasked with, a little lab techie, to come up with a sodium chloride solution that has a concentration with 3 sig figs of 1.00 molar. So what they did was they grabbed a 1 liter volumetric flask. You kind of see the calibration mark up here. So that's to contain, that little blue line right there, that's to contain 1.00 liters, I'm sure. So then they just needed 1.00 moles. So the molar mass of sodium chloride is 58.44 grams per mole. So they go ahead and they add this. Now what I think is wrong here is they probably should have added a little bit of water first because it kind of dissolves up better. Maybe they do in the next one. So they add some water, they swish it around, hopefully get it all dissolved, and then they bring it up to the right volume. And then it's very common mistake again. One more time, they need to mix it well. A common mistake is to do that last dilution and not to mix it. I've been there, done that. And then, of course, as you use it, if you don't mix it, then you, of course, have this is really concentrated, and this is dilute up here. That's not good. And then you're like, anyway. Okay. So this is the first of 2 assignment slides we're going to get to today. So just, I know. So this will be due after Thanksgiving. You have a whole week to do these. But you can knock them out today if you want to. So this is what these look like. 1359. Okay. So 59 is molarity, 61 is molarity, and 63 is molarity. But you know what they all have in common? The answers are in the back of your book for all these because they're odd problems, not as an odd strange, but so be sure and show off your work. So I gave some hints, you know, what is molarity? It's moles of the solute per liter of solution. But notice what they did in the first one is you don't have to go from grams to moles. They already have it in moles. So it's I don't want to say it's not too bad, but it's not too bad. Basically take that first number, and the mole number, and divide it by the volume. I kind of highlighted A there, though. A is one of those where the volume is not in liters, it's in milliliters, so you're going to have to fix that.
Yeah, that's really good. I
What's-
was gonna ask, since it's not in milliliters,
Yeah.
you have to do the second step.
Yes, yep, I want to do this right here. And then 61 takes it up a notch, where now the solute isn't given in moles, it's given in grams. So since it's given in grams, you have to get to moles. Yeah, and you're going to use the molar mass, exactly. So this up here in green, and I'll push these out on your Twitter feed. So this up here in green is actually kind of what I did right here. So if you just go ahead and take the grams divided by the volume, and then go ahead the next term, use your molar mass term. If you do it the flipped one, then your grams cancel, you're left with moles per volume. So that's kind of what I did here. And then don't let C throw you off. Now in this case, the mass is given not in grams but milligrams. So don't forget that 1 gram is equal to how many milligrams? Yep, 1,000 milligrams. So you're going to have to put that somewhere in there. And then the last one, let's see what I have for hints. I kind of wrote it all out for you. So the last one, the solute is sodium chloride. And again, we want molarity. And you're given grams, so you're going to have to go from grams to moles using the molar mass of sodium chloride. And then the third term up here is to fix that milliliter term that's on the bottom. Okay?
Does it matter the order that we put it in?
No, it totally does not.
As long as we have all of the terms?
Yep. Yeah, sometimes, I'm just kind of, I've done these for a while now, so I'm kind of have a way I do it, but no, it really does not matter. Okay. So the other type of problem I want to do today is this one. So hopefully you buy that sometimes you need to know how concentrated a solution is. I don't know if you do or not. But if you know how concentrated a solution is, you have units of grams per milliliter, or excuse me, grams per liter or moles per liter, okay? And you can actually use that concentration as a conversion factor. So I'll kind of talk you through that. So for instance, if you have it in grams per liter, okay, you can take let's see, how do I want to say this? If you want a certain number of grams, I'll put it over 1, you can use your grams per liter, I'll put liter per grams, you can use your concentration to get to liters. Okay, so that's your concentration, okay, and this is your goal. Similarly, if you want a certain volume, I'll go ahead and just put it liters, that's what you're after. You can use your grams per liter to go ahead and get to grams. Wait, no, you know the volume, yeah. Anyway. And I'll kind of show you down here what we do with molarity. If you know the moles and want to know what the liters are, we can use molarity, which is moles per liter. I'm going to do it upside down though. Moles per liter, I'm going to do liters per mole. And then moles will cancel. We're left with units of liters. Similarly, if you want to know the liters, we can do moles per liter. And the liters will cancel. And we're left with moles. Something like that. And don't worry about mass percent. We're not going to do that today, but we will next. We will after Thanksgiving. So kind of in a nutshell, that's what we're going to do. So we're dealing with a salt solution, and somebody went ahead and told us its concentration in grams of salt, grams of sodium chloride per liter of solution. Okay, now right off the bat, we're going to have to unpack that G/L, and that's on the next slide. So this one, actually, when we work it, our first term is going to be that 22.3 grams over 1, and then we're going to use our concentration as what we say conversion factor to get from grams to liters. So it kind of reminds me of density. When we did density before, density is in grams per milliliter, and I always said you always have to unpack that. That's grams per 1 milliliter. And so the same thing here. So 14.3 grams per liter means 14.3 grams of NaCl per liter of solution. And kind of what we did with density, we could like flip it, and we could also flatten it out. Okay? So for this particular solution, 1 liter contains 14.3 grams of NaCl. And for this particular solution, 1 liter solution is equal to 14.3 grams of NaCl. So all that stuff is true about this solution. So we're just kind of setting it up to be our second term here in a minute when we start with that 22.3 grams, whatever it was. I can't remember what it was. But when I grade your homework and your test, if you have a question like this, I am looking for that ratio to use it in your problem. So if we were to kind of map out this problem, it looks like this. We're going to go straight from the grams of NaCl to the liter of solution using the concentration that was given. And I just went ahead and flattened it out here so we can go ahead and make whatever ratio we need. So the first term is the thing we want to convert, and we put it over 1. That's that 22.3 grams of NaCl over 1. So this is again then, so if I put this over 1, if I make my next term, I want grams of NaCl to cancel, and I want to be left with liters of solution. So what does that ratio look like? Yep, 1 on top and 14.3 grams of NaCl on the bottom. That's it. So our grams of NaCl cancel, we're left with units of liters of solution. How many sig figs? 3. Yep. So I got 1.56 liters of solution. And this actually could be a practical thing. Say you're calling for, you have a process that you know that you need 22.3 grams of pure sodium chloride, and all you have to work with is a solution. And you don't have a way to measure the mass of I should say, you have a way to quickly get to the volume of solution. So you just need to have 1.56 liters of the solution, and you will have 22.3 grams of NaCl floating around in there. Okay. So just kind of a reminder, there are times in some chemistry problems where you need to be very explicit, okay? So just kind of remind you. An example of that is, for instance, when you guys were doing your stoichiometric calculations and you had the heart of the calculation where you're going from moles of something to moles of something else, okay? They were both moles, but what was different was they were moles of what? That you had to be explicit, so that's all it is. Okay, so let's do another one. So this isn't sodium chloride. This actually, so we did nomenclature in here last unit. This is potassium dichromate. K2 is, potassium is a +1, and dichromate, Cr2O7, is a -2. So notice we know the concentration not in grams per liter, but in moles per liter. The big M stands for molarity. So on the next slide, we're going to unpack that big M. Okay? So you can't work a problem 0.255 M. You have to unpack it. Moles of K2Cr2O7 per 1 liter of solution. So now this is where, and I think you're going to see it here in a minute, I would probably I can diagram it. It says if an experiment calls for 0.15 moles. So that's actually what we're going to start with. Okay. How many milliliters, question mark, milliliters is this? Given that, based upon its concentration, 1 liter is equal to 0.255 moles of the K2Cr2O7. That's exactly it. Looks like I'm going to have to fix something from liters to milliliters, aren't I? Okay, so here's unpacking. Here's unpacking at you. So don't use the M. There should be no big M's in working your problems. What it means is 3 things. 0.255 moles per 1 liter. And to me, I'm kind of forgetting the K2Cr2O7 because we only have 1 solute here. So 0.255 moles per 1 liter. 1 liter over 0.225 moles. Flatten it out. 1 liter is equal to 0.255 moles. Okay. So we're going to go from moles to liters of solution using molarity. Moles of K2Cr2O7 to liters of solution using 1 liter solution is equal to 0.255 moles, or 0.255 moles K2Cr2O7. But there's one more last little kicker. We wanted the volume not in liters, but in milliliters. So we're going to have one more term there. And that last term is going to use the whole 1,000 milliliters in 1 liter. And then we'll be done. So the first term is going to be, bless you, the 0.015 mole over 1. And then we want moles to cancel, be left with liters. So what does the next term look like? What do you think?
0.255 moles on the bottom.
Mm-hmm.
of the 1 liter.
Yep. 0.255 moles on the bottom, 1 liter on the top. And then we're almost done. We just need to fix our liters to milliliters. So what does the last term look like?
1,000 milliliters on top.
Yep, 1,000 milliliters on top. You look like heck, Becky.
Huh?
You look like you don't feel good. You're fighting a cold.
I know. Yeah. I wasn't gonna come to school today, but I got a test next period. So.
Ah, who gives a test on the Monday?
I had a test in biology this morning.
Silly? Oh.
Yeah, Celine.
Miss Slaymar had one this morning.
Okay then. I don't feel so bad.
I was okay.
You have
though. I'd rather do it
test
now.
tomorrow?
Yeah. The study for it.
That is so terrible.
I didn't study it at all. I didn't look at it.
I don't know what.
How many sig figs do we need to round this to?
2.
Why 2?
Because the 0 before the 1 is the placeholder.
Yep. Yep. This one is only 2 because there's two sig figs there, and you're right, there's 3 here, but we're always conservative. Yep. Cool. So I got 59 cute little milliliters. Cool. And I think there's only one more problem. There's 2 more problems. Oh my gosh. Okay. Well, with all that testing going on, I don't feel so bad. We have 2 more problems to get under your belt before that last homework assignment. Okay, let's do another one. Now, if you ever get stuck, you're kind of seeing a pattern what I do, but you don't have to do it in the same order. But I usually keep that till last. I usually keep that as like near my last term-ish. I don't know. And then my first term is going to be the other thing that I didn't. That's not molarity or not solution concentration. So if I start with milliliters, okay, and I know I'm going to use molarity, which is moles per liter, I'm going to go from milliliters to liters. I'll fix that first. And then I'm going to go ahead and insert the molarity. I'll go ahead and say it. I'm going to insert 1 liter is equal to 0.108 moles right there. And then actually, that is what I'm after, so question mark moles. Okay. So, we're going to, this actually is what I just said, but it's fancier. So we're going to go from milliliters to liters, because we can't use molarity with milliliters. And then once we're at liters of solution, we can use molarity to get to moles of, in this case, calcium chloride, CaCl2. So, first term, It's gonna be that, with 3 sig figs, 75.0 milliliters of solution. What's the next term gonna be?
1,000 milliliters on bottom.
Yep, very good. 1,000 milliliters on bottom, 1 liter on top. Perfect. So now I didn't unpack it for you here, but what do you think, what's the next term gonna be?
0.
Is that going to,
108 mole.
Yeah.
on top?
0.1.
On
Mhm,
top, yeah.
on top, you got it. 0.108 mole calcium chloride on top and 1 liter on the bottom. And that should give us moles. Units of moles. So how many sig figs?
3 times 3.
Why 3?
Because 0.0, that counts.
Yes, that counts. 3 sig figs. Yep. And this is one of those tricky ones. To give it 3 sig figs, remember that these zeros, they're placeholders, they're important, but they're not significant. And the 8, 1, and we have to actually remember that's a trailing 0 after the decimal to give us 3 sig figs. Okay. Okie dokie. Another? Another one. Back to sugar solution. Okay, so the C6. Well, no, this is. Wait a minute. Okay, the other one must have been something else.
Sucrose.
Yeah, sucrose. This is glucose. Thank you. Okay, so what mass, so we'll do that. So question mark grams, what mass is in 125 milliliters? So I'm going to start with 125 milliliters of, and there's the molarity. Now that molarity means 0.432 moles for 1 liter. Now this is one where, do you see we can go from milliliters to liters, okay, using the 1,000 milliliters in 1 liter. And then we can go from liters to moles using molarity. And then we can, how are we going to go from moles to grams?
Molar mass.
Yes, using mm. That's exactly it. All right. So execute. Okay, so our first term is going to be the milliliters. 125 milliliters over 1. And then what next?
Then 1,000 milliliters on bottom.
Yep, 1,000 milliliters on bottom, 1 liter on top. Then what next?
Uh, 0.432 milligram on top.
On top, I like it. 0.432 moles on top and 1 liter on the bottom. Perfect. Now I see an error here because I don't have on my slide what the molar mass is, do I? So do we use the flipped version or the non-flipped version of molar mass? the not molar mass as it is, the non-flipped version. Yep. So if you were to go ahead and do a little side calculation, you would come up with 180.16 grams per mole is the molar mass. So 180.16 grams over 1 mole. So if we kind of go along and make units cancel, the milliliters cancel, the liters cancel, the moles now cancel with that last term, and we're left with units of grams, which is wonderful. Phew. All right. So how do we need to round it?
3 6 figs.
Yep. That's what I got. So 9.73 grams of glucose.
And we didn't use the molar mass in the last one because we were trying to find grams here, right?
Right.
Last one we were trying to find moles.
Yes, yep. Sometimes it's hard, it's tempting to stick in that molar mass when you don't need to use it. That's a good point. Okay, so I don't know if your slide says it in your notebook, but don't do 65 and 67, but you need to do the other three. Take a quick look at those. This is what they look like. All right. Fun and games. And notice they're all odd again. So you can actually check yourself, which is kind of nice. But I'm thinking they don't always have the right answer. They don't round correctly sometimes, though. Okay, so the first one, here I gave you a hint. I just kind of, again, I'm going to push this out under Twitter. Let me know if you can't find it. But we're after the mass, so I put grams at the end. And notice the volume of the solution's 35 milliliters. I put that at the beginning. And again, we're given molarity. Hey, this is like the one we just did. Yeah, just exactly. So we had to go from milliliters to liters, and then we could go from liters to moles using molarity, and we can go from moles to grams using molar mass. The next one, it's like the same pattern. This is like so boring. Okay? The next one's finally a little different. So 73 is the same deal. So for 75 question mark liters, and they give us the molarity, and we want to ultimately know liters to get 1.5 kilograms of sucrose. So I would start out with my 1.5 kilograms of sucrose. That's your pure solute. Kilograms won't work, so you got to get to grams. And how many grams are there in 1 kilogram? Yep, very good. And then once you have it grams, you can get to moles using the molar mass. And then once you have moles, you can use molarity to get to liters. So that one's a little more different, a little different. Okay. Any questions? Cool. Well, that's all I got. So have a great Thanksgiving.
You too.
Thank you.